Good morning, everybody. I'm Mike Griffin, and I'm happy to be here this morning at another of our Aeronautics Research Mission Directorate technical seminars. I think most of you, both in the audience here and the far larger group out there online, know that I've been real pleased with Lisa Porter's reintroduction of technical sanity to at least some aspects of headquarters. One of those things being roughly monthly, but at least more than semi-occasional, purely technical seminars here at headquarters. I think it's time for us to remember what we are in the end all about, and that is flight in all its forms, and these seminars provide a good way to remind ourselves of that. This morning we have Dave McNally, who's going to talk to us about air traffic management problems associated with what will be the next generation air traffic management system. Dave is from NASA Ames. I just found out he's been there 23 years, which means he was there long enough ago to buy a house and not have to mortgage his unborn children to get it, speaking as a former Californian. Dave is Associate Principal Investigator for Separation Assurance on the NGATS program, where NASA is a partner with FAA. As I mentioned, he's a longtime resident of California and NASA Ames. Got a bachelor's and a master's degree in mechanical and aerospace engineering from UC Davis, and has published 27, I think it is, technical papers in GPS landing and navigation and air traffic management. So we have a real technical professional at NASA to talk to us today, and I'm pleased to sit in the audience with the rest of you and hear him. Dave?
Thank you, Mike.
It's all yours.
Thank you. Well, good morning, everybody. I want to thank you for the opportunity to be here. It's quite an honor. So can we have the first slide? So as Mike said, I will be talking about trajectory-based automation for separation assurance in the National Airspace System. Next slide. So first of all, just an outline of my talk. I'd like to lay out separation assurance in today's operations and try and describe how things work today, describe the air traffic control system, and specifically how separation assurance works, and then briefly talk about the expected increase in air traffic demand in the coming 20 to 25 years. And that really is the two of those items is the basis for the motivation for this work. We just don't see that today's air traffic control operations will support a substantial increase in air traffic. So the main part of my talk, I'll be describing the technical challenges and then going into detail on some of the research areas that we have been working on in order to address the problem. And following that, I will conclude. Next slide. So how does the air traffic control system work? First of all, the picture shows just a snapshot of air traffic in the United States. All the yellow targets are flying aircraft. The picture is about 5 p.m. Eastern Standard Time on a typical day in the summer. In the picture, there are about 5,000 aircraft flying throughout the day. Throughout a normal day, there are anywhere from 3,000 to 5,000 aircraft flying in the NASA at any given time. So the primary purpose of the air traffic control system is really, it's twofold. First, keep aircraft safely separated. That is the #1 reason for the air traffic control system. And what we call that function is separation assurance, and that's what I'll talk about today. The second function is to minimize delay, and what that's usually called is traffic flow management. There are often things that come up in the air traffic. Air traffic control system is a highly dynamic system. there are things that come up that tend to generate delays in the system, severe weather being one of them. So there needs to be functions and automation in place in order to minimize delay and keep aircraft flying on their most preferred route in the presence of these problems that come up. Another common problem is busy airports. There are too many aircraft approaching a busy airport, more aircraft that the airport can actually handle. And there's NASA-developed technology being deployed right now to help solve that problem. So these two problems are really the primary focus of today's air traffic system and any air traffic system, even the future air traffic system. These are the primary problems, and we want to do all this while being while focusing on the preferences and desires and the users of the airspace. So now what I'd like to do is, well, first of all, let me say I'd like to talk about how the separation assurance functions are sort of separated amongst the roughly 14,000 air traffic controllers that work for the FAA today in about 300 air traffic facilities. Next slide. So the graphic shows how the airspace is generally divided up. Of course, it's very familiar, surface operations, terminal, and route. Surface operations, of course, are when the aircraft are on the ground. Terminal operations are from takeoff to roughly 10,000 feet as the aircraft makes its way up into the en route airspace, which is roughly about 10,000 feet and up. And the point of this slide is as the aircraft transitions from its origin to its destination, there are numerous air traffic controllers that are in constant communication with that aircraft. A typical flight across the country, the aircraft will probably be talking to about 5 or so air traffic controllers or air traffic control teams in the surface and terminal domain, and another 20 or so air traffic control teams in the en route domain as it flies across the country. And again, as the aircraft is landing, there's another 6 teams of controllers that the aircraft is talking to during the descent and landing phase. And so the way the airspace is divided up so that controllers can divide up their responsibility is into, I'm going to kind of start focusing on the en route airspace now, is into what are called centers and sectors. An airspace sector is the smallest unit of airspace, and there are 1 or 2 controllers responsible for safe separation within each airspace sector. Next slide. So this is a picture of the airspace in the United States. The white boundaries are the center boundaries. There's roughly 20, or there are 20 centers in the continental United States, and each center has 40 or so sectors within the center. And these centers are buildings that are located in various places with a few hundred air traffic controllers working in each one. Let's go ahead and roll that movie. So as an aircraft is flying, what you see is the red sector is the airspace sector that currently has control of the aircraft. As the aircraft flies across the country, transfer of control is effected through radio communications with the pilot and the air traffic controllers in the sectors. So as you can see here, you can see a number of sectors, and you might even notice that in some of these sectors, the aircraft is only passing through a little corner of the sector, and there are special procedures to handle aircraft that are just kind of cutting a corner. And so the idea is that there's just this constant transfer of responsibility from one sector controller to the next as the aircraft flies. So Okay, so now I've shown you one aircraft flying across the country. What makes the problem hard is there are thousands of aircraft flying at any given time. Next slide. So this is the picture I showed on an earlier slide. This is an animation, and so before I run this, let me set this up. What you're seeing is this will be a 24-hour animation of all aircraft flying in the National Airspace System. This was July of 2005. Right now it is 8 p.m. Eastern Standard Time, and there are probably about somewhere around 4,000 aircraft flying. So let's go ahead and roll that movie. So as you can see, it's the point of this is it's a very highly dynamic system. These aircraft are constantly flying, and of course the air traffic control system its job, as I said, is to ensure safe separation and to minimize delay in the presence of problems. In the upper right part of the screen, you can see all the traffic going over to Europe. It's probably, what is it? Okay, it's 1 in the morning, 2 in the morning now. The traffic is probably down to about 800 or so aircraft. On this day, the minimum number of aircraft flying was about 800. We're 4 in the morning now, so the East Coast is starting to wake up. You can see the traffic building on the Northeast Corridor, which is roughly between Chicago, Boston, Washington, Atlanta, and that's the very, very heavy traffic area. I guess it's obvious, but by the way, the red outlines are the states, and the blue outlines are the sector boundaries. So at about 4 or 5 Eastern Time is the maximum number of aircraft on this day was about 5,000. I think this is a typical day. You can see the flights coming in from Europe now, and a lot of activity on the West Coast. So the point of this slide is that this movie is that it's a highly dynamic system. Some of these aircraft are on their route, some of them aren't. What's not shown here is many of these aircraft, probably half of them, are climbing and descending, not just flying straight and level. It's the transitioning, the climbing and ascending flights that add quite a bit of complexity to the problem. So, okay, so let's go to the next slide. Okay, so weather, of course, severe weather makes the problem even more complicated. This animation here is a 12-hour period in and around the New York TRACON. So the blue streaks are tracks of aircraft with about a 20-minute time history on the track of aircraft landing in the New York TRACON, and then the other streaks, which are kind of faintly visible, are all the other traffic. And so you can see a lot of aircraft going into holding patterns. What makes this complicated is severe weather is very difficult to predict. And so therefore a lot of trajectory changes need to be made at the last minute. And why is this important to separation assurance? Because when aircraft are changing trajectories in order to maintain separation, you need to make sure you're not flying into a severe weather cell. And so the modeling and analysis of these of severe weather, which is, as I said, is really the major cause of delay in the system, is a really critical part of this activity. Okay, let's go to the next slide. Okay, so 2 slides ago I talked about airspace centers and airspace sectors. This is the Fort Worth Center that I'm showing here in the white outline, and what I'd like to use is one of the sectors in Fort Worth Center to just really try and describe how separation assurance works in today's operation. So one of the sector down there in the lower right portion of Fort Worth Center is the sector I'd like to use. The reason I chose this sector is because there's a complex mix of aircraft departing from Dallas-Fort Worth, departing out. Dallas-Fort Worth is right in the middle of the picture here. Departing from Dallas-Fort Worth, climbing through this airspace. There's another stream of traffic, which is kind of the very bottom of the picture, just a bit off center to the right, are the Houston airports. They're also climbing through this region. So I've got a mix of climbing aircraft from major airports. I've also got multiple streams of arriving aircraft coming through this sector and all the overflights. So it makes for a sort of a rich, complex mix of traffic that is important to keep in mind in the separation assurance work. So why don't we go to the next slide? Okay, so this is an animation, and I'll start it in a minute, but really this is where I'd like to describe how an air traffic controller in today's operations maintains safe separation. So let's go ahead and roll the movie. Okay, first of all, the blue outline is the airspace sector boundary. The air traffic controller is responsible for the safe separation of all the aircraft within that airspace sector boundary. Now, this display here is very much like, not exactly, but it's very much like what a center controller or any controller is looking at. The primary pieces of information on the display are the radar targets. The radar track positions of the aircraft. Those are shown in, you can see the target position, and then the fainter histories behind the target are the last 3 track histories of the particular aircraft. Now, each aircraft, of course, has a flight data block associated with it, and that's how the controller knows the call sign of the particular aircraft. The one right in the middle, there's a target right in the middle heading about to the kind of in a northeasterly direction under the green. Oh, by the way, the green targets are arrivals to Dallas-Fort Worth. The blue targets are departures from Dallas-Fort Worth, and the white targets are everything else. We just color code them for ease of analysis. So each one of those targets has on it the call sign, the actual flight plan altitude or the intended altitude of the aircraft, the actual altitude of the aircraft, which is based on Mode C pressure altitude returns that come back from the aircraft along with the radar data, the ground speed of the aircraft, and the aircraft type. So what the controller is doing is visually scanning this display, and in their mind, the ring on that aircraft there is a 5-mile range ring, so it's got a radius of 5 miles. What the controller is doing is visually scanning this display and looking for potential conflicts. A conflict is when 2 aircraft look like they might come together and violate the safe separation criteria unless action is taken. Safe separation criteria in en route airspace is 5 miles or 1,000 feet. In the terminal area, it's 3 miles, and that's due to the fact primarily that the radar sweeps in the terminal area update every 4.5 seconds, and the radar sweeps in en route airspace update every 12 seconds. So what the controller is doing is looking at all these aircraft, deciding if any are predicted in conflict, in other words, predicted to lose separation unless some action is taken, and then providing through radio communication with the pilots, they will provide clearances to the pilots. For example, an aircraft might be told turn 30 degrees left, vector for traffic, or one of those climbing aircraft may be in conflict with a level aircraft or another aircraft. They may be told to level off at a temporary altitude while the conflict aircraft passes over. So, question is, one of the questions is, well, how many aircraft can a controller handle? Can a controller safely handle? In fact, every sector has a number. It's called the monitor alert parameter, and that is the number of aircraft that the controller can be expected to handle in that particular airspace. It's generally around 15 aircraft, plus or minus, depending on the complexity of the traffic. In this particular sector, the monitor alert, or the maximum number of aircraft that the controller is expected to handle, is 13 aircraft. So one of the things that is done in the NAS, if any if sectors are predicted to go over their monitor alert parameter, actions are taken to either divert aircraft or route them around the sectors. Let me just say a bit about, there's some automation available. Conflict alert, which I'll show some data on later, is a legacy automation function that is looking at making a projection of the aircraft trajectory based on 2 or 3 track hits. So if any of those aircraft are predicted to lose separation within 2 or 3 minutes, those data blocks will start flashing, alerting the aircraft to the potential problem. There are other trajectory-based automation systems that have been developed and are working in the NAS. They're not working on the radar controller's display. They're working on an auxiliary or what's called the D-side radar associate position that make use of higher technology or trajectories. So the big problem, to close on this picture, the big problem is that we know that this method by which separation assurance is assured, by which aircraft are kept safely separated, will not support a substantial increase in traffic. And that is really provides the motivation for this work. Next slide. So this is a plot of the scheduled revenue passenger kilometers as a function of time. And the point of this plot, and you can see the blue line is North America, the red graph is Europe, and the green is Asia and the Pacific. And the point of this picture here is that air traffic has continually been rising over the last 30 years, even in the presence of big problems like the oil crisis and like September 11th. Air traffic continues to rise, and all of the projections for the future is that that trend will continue, and thus the projections are a big increase in traffic in the next 20 years, probably two to three times. And as I said, today's airspace system will not support a substantial increase in traffic. Next slide. Okay, so what is the effect of an increase in traffic? These two movies here just kind of give you an idea of what a 2.5 times traffic might look like in that airspace region, which I described a minute ago. So let's go ahead and roll that movie. What you see here is, first of all, the yellow circles are when 2 aircraft are predicted to come with between 5 and 10 miles of one another. And the red circles are when 2 aircraft are predicted to pass with less than 5 miles. Now this is a simulation, so we've let the traffic run what we call open loop. So there are no controller inputs. We let the traffic fly into the region, and we let it fly open loop. And this sort of represents, well, what's the problem that the separation assurance system has to solve? It has to make sure that there are no red circles up there. It has to make sure that none of those aircraft pass with less than 5 miles. And as you can see, the traffic on the left, there's quite a bit fewer problems in the traffic flowing in today's traffic levels, whereas the one on the right, showing roughly 2.5 times today's traffic, there's a substantially higher number of potential conflicts that have to be resolved. So now what I'd like to do is start talking about what do we think the solutions might be. What's our technical approach to solving this problem? Next slide. Okay, so in this slide, I kind of want to talk about the elements of a future airspace system. This is not. This looks like an architecture, and it's the start of an architecture, but I really use it to talk about the elements of the airspace system and how they might play together. First of all, the green box on the left, the trajectory automation box, that is really the workhorse of of the system. There needs to be a trajectory-based automation system that is working to solve most problems, to identify most conflicts, to respond to pilot requests, to support the air traffic controllers for off-nominal situations, to really handle most of the separation assurance problems. And these problems are dealt with on roughly a 2 to 20-minute time horizon. The basic idea is that you want to solve most traffic conflicts well before they become tactical. I mean, the goal here, I show it as 2 to 20 minutes, but the goal in that trajectory automation box is to solve most problems 4 or 5 minutes before they become tactical. Now, one of the key points of this is that trajectory automation function can support multiple levels of automation. You could have partially automated analysis being supported there. You could have analysis of pilot requested trajectory changes sent down over a data link being supported by the trajectory automation function. You could have analysis of controller generated trajectory changes being supported by the trajectory automation. The point is, it's a common trajectory analysis capability that serves all the levels of automation, and that is key for coordination and consistency. Now, the red box. We understand that there needs to be a safety critical function that is looking at a very short time horizon, and this is a simpler automation function. It is looking out at a short time horizon. It is looking for multiple trajectories. Its sole purpose in the system is to look for cases that have somehow been missed by the primary trajectory engine and identify those cases at a very highly safety critical level. We think the data link will be an important element in a future NAS system, and really at the bottom is the whole function is the generation and the maintenance of a set of conflict-free trajectories. And one thing I should say about conflict-free, that applies to, it's not only conflicts that are detected that come up, but it's trajectory, the same system supports any trajectory changes that are input by the airspace user. I want to change a route. I want to fly at a different altitude. For any reason a trajectory needs to change, the system needs to support that. So there's another important element in this automation that I want to talk to next. Next slide. So another approach to this, and we think a complementary approach, is to take the trajectory automation and the safety assurance automation and put it in the aircraft. So in the 3 aircraft in the upper left of the slide here, I've shown them with similar kinds of automation. These aircraft are supported by an ADS-B system where each aircraft is transmitting its position and velocity, in other words, its state vector and its intent. And it's transmitting that out to all the other aircraft in its vicinity. And so those aircraft, each aircraft that is so equipped could have a system on board that autonomously detects traffic conflicts and uses trajectory automation to solve the problems. The little halos above those aircraft represent they represent a data link function, although it is a transmit function. It doesn't require the two-way handshake of the data link shown in the lower part of the diagram. So what we really think is that in the end, in order to maintain the safety of the system under the variety of conditions, including uncertainties and failure modes and everything else, that it's going to come down to a combination of these automation functions both in the ground excuse me, and in the air that will make this system work. One more point I want to make about this slide is that I haven't mentioned yet the traffic alert and collision avoidance system. The so-called TCAS system is a system that has been flying on most commercial airliners today, and its purpose is to prevent collisions in case all of the separation assurance functions have somehow failed. TCAS is there to prevent collisions. And so this diagram I show here is it's really a layered system of separation assurance functions. It's a primary function that tries to solve problems 4 or 5 minutes before they become serious. It's a second safety assurance function, the red one, that maintains separation at a very high level of safety criticality. And then finally, there's the TCAS system that is still there and would operate much the same as it does today. So it's how do these three systems kind of play together in order to maintain safety in the system with a substantial increase in traffic. So what are the sort of the top level challenges that we see here? Next slide. First of all, the allocation of the automation functions between the automation and the human operator. We don't anticipate that all of this will be fully automatic, though we believe that there will be much higher levels of automation, and in some cases it will be fully automatic. So what is that allocation of functions between the automation and the human operator that maintains safety under all conditions, including failure modes? The next technical challenge is the automation of the conflict detection and resolution. We're in the process of developing algorithms to automatically resolve conflicts. In other words, automatically generate conflict resolution trajectories that are safe and that are minimum delay. That is a challenge given all the complexities of the system: climbing aircraft, descending aircraft, level aircraft, aircraft on their route, off their route, uncertainties. It makes it challenging. So the next big challenge is, of course, the allocation of the automation functions between the cockpit and the ground. I mentioned that I think it's going to come down to a mix of this automation. And so, what is the right allocation? And finally, fault-tolerant system integration for safety. We need to have a fail operational system. There are failures, and we need to ensure that we maintain safety in the presence of failures. We can't just hand the control back to the air traffic controllers and expect them to do it the way they do it today when they've got 2 or 3 times the number of traffic in their airspace. And so now, what I'd like to start doing is going down a little deeper into some of the work that we're doing. But first, I'd like to talk about trajectory and conflict analysis of what is a 4D trajectory, which is really the basis for this work. Next slide. Next slide. Okay, so here's a little piece of airspace with just a snapshot of the airspace with a bunch of targets. This is the airspace I've shown earlier. And so there are basically 4 pieces of information that we need to build a 4-dimensional trajectory for every aircraft. And a 4-dimensional trajectory is a prediction of that aircraft's X, Y, and altitude as a function of time. Being able to predict and maintain these 4D trajectories is fundamental to automation based on trajectory analysis. So the 2 pieces of information I'm showing on this slide are the fundamental ones. We always have the actual position of the aircraft, the track position of the aircraft, and its flight plan. The green line there is the current flight plan of the aircraft. So the next most important piece of information is the wind. Next slide. So in order to generate a 4D trajectory, we have to merge the track information, updated every 12 seconds, with the flight plan information, updated periodically as flight plans are changed or modified, with wind information. That particular wind there is about 100 knots out of the west at 35,000 feet. So we combine these three pieces of information with aircraft performance models in order to get a four-dimensional trajectory for every aircraft in the airspace. Next slide. So the white line I'm showing there is our four-dimensional trajectory for this aircraft. This particular aircraft is climbing out of Dallas. It's you can see kind of in the middle of the white line is its predicted top of climb. So it's got about, not sure how many minutes. Looks like it's about 12 minutes to the predicted top of climb. So once I have a 4D trajectory for all of the aircraft, I can do a lot of things. I can conflict detection is one of them. Automation for arrival metering is another. It's a common trajectory analysis capability is really the basis for all of this automation. So what I'd like to talk about is, of course, here is the conflict detection part. If I have a 4D trajectory for all the aircraft, I compare those trajectories against one another and identify potential traffic conflicts. Next slide. So here's a conflict list, and what the list shows is the aircraft pairs that are predicted to come into conflict over the next 15 minutes. The columns of numbers in the picture there, the first column is the time in minutes to first loss of separation, and the second two numbers are the minimum predicted vertical separation and minimum predicted horizontal separation. So the first pair in the list they're predicted to lose separation in 5 minutes. They're flying at the same altitude, and their minimum predicted separation is 1 mile. So this is a problem that will definitely have to be dealt with. The second pair in the list is the one aircraft, as indicated in the list, that is descending, and the one aircraft is level at the point of first loss of separation. The final column in the list here is an indication of the automatically generated conflict resolution trajectory, and I'll talk about that more later. So let's go to the next slide. So when there's a conflict, now what I'm doing is showing you, I'm kind of walking through the manual use of this automation system. So when there's a conflict, the user might click the list there and bring up the graphic display, and you can see a nice graphical representation of what is going on. A key part of the trajectory analysis capability is what we call the trial planning function, and that's really the essence of the conflict resolution capability. Next slide. So what I really need to do when I have a traffic conflict, I need to, number one, I need to solve the conflict, and number two, I need to make sure that I have not created any other conflicts. And so I have a trajectory analysis capability where here the yellow trajectory is dynamically generated either by the automation or by the air traffic controller, and that is continually probed for conflicts with all other aircraft. And in a minute, I'm going to show you in a minute how this looks dynamically. But the idea here is that when that trial plan comes up, that is continually probed against the conflict aircraft and all other aircraft. And when there's an indication that it's clean, then we know we have a new conflict-free trajectory. Next slide. Okay, so this is a movie. Why don't you go ahead and roll the movie? And so what you're seeing, you see the clock ticking off on this is a real-time movie showing the point of this is to really show you the dynamics of the system. You see the conflict list up there. This is being manually driven. The conflict graphics comes up. Now I'm going to activate the trial planning function and select an auxiliary waypoint dynamically. And first I'll try and turn inside and see if I can turn behind that traffic. That's usually a reasonable maneuver. And again, okay, now there, I've detected another conflict. The idea is that this system is highly dynamic. I'm detecting conflicts. As I move it, I'm updating my track position, my aux waypoint position. There I've detected yet another conflict. And so it looks like a left-hand turn is not going to be workable. I try moving in the other direction. I'm doing this kind of slowly here to try and illustrate the the dynamics of the system. That, again, that trial plan trajectory is updated every 1 second, so you get a very rapid feedback of the analysis. Okay, now I've got a clean trajectory. If I like that, I'll go ahead and accept that. And another point I'd like to make on this one is that this can be run either manually, as I've sort of illustrated here, or it can be run under the hood automatically. But the trajectory analysis capability is common, and so that is very, very key. Okay. I talked about uncertainty. We always have to deal with trajectory and uncertainty, and that comes through in the trajectory models and in the conflict detection. Next slide. So this is a typical uncertainty histogram showing uncertainty level for level flight aircraft with a 10-minute prediction. And so as you can see here, there's the So the idea is that we're analyzing 1,200 aircraft that are actual aircraft flying in the NAS, and we're making a prediction 10 minutes out, and then we're seeing how well was our prediction. And so you can see that the mean error is near zero, 0.3 of a mile. Our standard deviation is about 3 nautical miles, and the point being here is that standard deviation is really on the order of the separation criteria. 3 sigma is 9 miles, and our separation criteria is 5 miles. So that needs to be folded into our automation capabilities. I haven't talked about it, but all of the conflict detection has probabilities associated with it based on these kinds of uncertainties. The histogram is a little flatter, reflecting higher uncertainty for aircraft that are climbing. Okay, next slide. Okay, so what I'd like to talk about now is the levels of automation. In this slide, I sort of describe what you can imagine as 3 levels of automation in a highly automated separation assurance system. The first level you might imagine is that the automation system detects the problem and generates a list of conflicts like I showed earlier, and that the human resolves the problem using some kind of trial planning function like I showed. So the next highest level of automation might be, well, the automation detects the problem and suggests a conflict, and then the human looks at the suggestion and modifies it as necessary or as they see fit, and inputs the solution. And of course the highest level of automation is the automation detects the problem and the automation resolves the problem. So what I'll talk about, I'll show you some results here in a minute of the first level, the automation detects and the automation resolves, and then later the second level, and then I will close with a description of some of the work we're doing in safety assurance. Next slide. Okay, so we've done some experiments recently which really kind of look at the use of the trajectory. The question is, if we use the trajectory automation capability we have right now, if the controller, if a human controller were to respond to only those conflicts detected by the trajectory automation, could we maintain separation in the NAS? Now that alone is a huge change in relative to today's operations. So what we've done here is we've set up a simulation. We've picked in this example we've picked 5 sectors where and we've run some real-time tests in the lab. So as the aircraft, we have a live. I should have mentioned this earlier. We have a live feeds of data, courtesy of our close collaboration with the FAA, from all the centers in the NAS, and these live feeds of data are just invaluable as a data source for developing and verifying all of this technology. So in this picture here, we've chosen these 5 sectors in the southeast corner of the Fort Worth Center airspace, and we take a live feed of data, and as the aircraft fly in, we sort of, what we want to do is we want to take control. We want a real data flow, but we want to take control of the traffic so we can provide the separation assurance. And we need to kind of take the actions of the real controllers and the real data flows out of the system. So as the aircraft fly in, we take control and we start flying these aircraft using a radar track simulator and the flight plan intent that they had when they flew into the airspace. In this experiment, the uncertainty of our predictions, our trajectory predictions, was roughly comparable to what we have today due to the fact that we were using two trajectory models for modeling and radar track generation. So the next thing we needed is I wanted an objective metric that I could use to compare today's the operations in the automated system directly to the operations in the real data and get a direct objective comparison. Next slide. So what it really comes down to in the airspace system is what was the minimum separation for every pair of aircraft in the airspace. And so this is a simple metric where we looked at every unique pair of aircraft in the airspace and we said, what was the minimum separation? Sometimes it's going to be 25 miles, sometimes it'll be 4 miles, sometimes it'll be 100 miles. But what I want to see, and so that kind of a metric, what I want to see is what that looks like over time in today's operations where the air traffic controllers are providing separation and in using the automation system where the automation system is providing separation. Next slide. Okay, so the way we ran the experiment is, again, we had 5 sectors, and what I'm showing here, we actually ran higher levels where we had more than 5 sectors and higher traffic densities. But I'll just show you this one. We had 5 sectors of airspace. We had a conflict list. The job of the air traffic controller here, which happened to be not a real air traffic controller but an engineer in our lab, was to respond to all the detected conflicts, generate a conflict-free trajectory, and implement that trajectory. And then the flight simulator would actually fly the trajectory according to the flight plan amendment. And a very simple task. And so what I'd like to do now is show you some of the results of this analysis. Next slide. So first of all, here is these data represent the operations of the actual operations, today's operations. This is, so you can see in the 90-minute traffic sample that we chose that in the 5 sectors there was roughly 30 or so aircraft in this airspace, plus or minus, and that there are a few times when aircraft were the bottom. Let me just say the bottom graph shows the number of instances where unique pairs of aircraft passed between 5 and 10 miles, and where aircraft passed with less than 5 miles. Of course, this is today's operations. No aircraft passed with less than 5 miles. The aircraft that passed with greater separation we're not showing on here. So you can kind of see that during most of the time there aren't any aircraft passing closer than 10 miles, and sometimes it pops up to where there are a few aircraft. So next thing I want to do is, the next one shows an open loop simulation. Next slide. Next slide. So this is if we run the simulation open loop and we put in no control actions at all, you can see that many aircraft pass with less than 5 miles. And in fact, that is the reason for the air traffic control system. There needs to be monitoring and inputs to ensure separation. Again, we ran the simulation here over 90 minutes with the flow through that piece of airspace, and this is what we get. So this is the problem that needs to be solved with the automation. Next slide. So here I show the metric. On the top slide, I show the separation metric for the automation, and where the pseudo controller, the ATM engineer, is simply solving detected conflicts and generating conflict-free trajectories, and you compare that to today's operations, and the point is that the separation characteristics are pretty similar. Okay, it's and really the bottom line here is that I've got one controller working 5 sectors doing the work of 5 to 10 people using trajectory-based automations, and I don't have any losses of separation. Okay, so now what I want to do is I want to look at a higher level of automation. Go to the next slide. Okay, so here at this level we are looking at the automation detects, automation resolves. And this is a big part of our effort. Notice I've indicated in the diagram in the upper left that the work that we're doing here could apply to a ground-based implementation, which is implemented via data link, or it could also apply to an airborne-based implementation. There needs to be automation that automatically detects and automatically comes up with a solution. Now, whether that solution is used exactly as is, that's a separate question, but there needs to be an automation function that comes up with trajectories that can be used to solve problems automatically. So really the logic comes down to questions of, given the airspace, in the diagram here, the 2 blue aircraft on the lower side they're the ones that's the primary conflict. Now the blue aircraft on the lower right also has a secondary conflict with the green aircraft coming in from the left. The dashed line is an initial cut at a resolution trajectory, but you can see that resolution trajectory creates another conflict with the orange aircraft coming up from the top. So the idea that what the automation needs to do is it first needs to decide given the situation, given the characteristics of this particular conflict scenario, which aircraft do I move? What kind of maneuver do I use? Do I go up, down, left, right? Do I use speed? And what are the constraints? And when do I issue it? Is it, if I've detected it 15 minutes out, do I issue it now, or do I wait? Do I wait until it's 8 minutes out? And this depends on a lot of factors. Metrics. What is the objective metric that I use to determine whether this is a good resolution maneuver or not? Firstly, it's safety. The maneuver has to be safe, but it needs to, you strive for a resolution that is close to or minimizes the deviation from the aircraft's preferred route of flight. There are airborne and ground-based methods. I mentioned that the logic we're developing can be used in both approaches. There will probably be little differences depending on whether the automation is implemented in the air and the ground. Those will be largely dependent on the type of surveillance and intent information that is available. What are the characteristics of the data exchange, and how are the trajectories coordinated? Okay, so we've done an experiment. In this case, we used Cleveland Center airspace. The reason we use Cleveland Center is because everybody always asks us, yeah, well, how does it work in Cleveland? That's the most complex airspace in the country. And so we're starting to take a closer look at the operations in Cleveland Center. Next slide. Okay, so I've shown, I guess everybody really knows where Cleveland Center airspace is, but it's inside the red circle there. So we've run a fast time simulation in the lab where we're looking at 24-hour traffic samples, and we're running the fully automatic resolution algorithms against these traffic samples. All aircraft are above 10,000 feet, and in this case there's no trajectory uncertainty. So the movie here, basically the movie, just kind of, I use it to try and give you an idea of the difference between the traffic complexity in 1 times traffic and that of 3 times traffic. In the analysis, as I'll show, we've done runs at 1 times, 2 times, and 3 times the traffic level. So go ahead and run the movie. It just runs for just a few seconds. It runs kind of fast, but you kind of get, on the upper left you see Detroit, the airports, Detroit, Cleveland, and Pittsburgh is down there in the lower right. Okay, next slide. Okay, so here's an example. I just want to give a kind of a typical example and one that illustrates a number of the factors that need to be considered in the automatic conflict resolution problem. The red and the blue aircraft are predicted, first of all, they are on a descent profile towards their meter-fixed crossing point. They're both crossing into the terminal airspace at the same meter fix where there's a restriction of 10,000 feet, 250 knots. The primary conflict is detected, you can see there, midway through the descent. And so the resolution, which is the green line, is it picks the blue aircraft because the blue aircraft in this case is behind and it's the slower aircraft, yet it detects a secondary conflict with the black aircraft. Now in some cases, in order to solve the immediate problem, it's okay to have a secondary conflict and you just treat it as another conflict that you have to solve later. In fact, that's pretty common in complex airspace for aircraft. They've got a conflict that's happening in 2 or 3 or 4 minutes. They got to move one aircraft. They know they're putting it in conflict with another guy, but they know they're going to move the other guy later. And this is very common in complex airspace. So basically what we've done here is we've generated the green trajectory, solves the problem with the red aircraft, the primary conflict, and maintains the meter fixed crossing restriction, but it generates a secondary conflict. And I won't show the data here, but the secondary conflict is resolved by moving the black aircraft. So I've got a couple of movies here that sort of illustrate the conflict problem and then the resolution problem. So next slide. Okay, so here's the conflict attack. First of all, the graph on the left, the main graph, it just is an XY plot showing both the aircraft coming together. The little bar on the lower right and will show the actual horizontal separation between the two aircraft as they progress along our predicted trajectory. Now the bar on the right shows the vertical separation between these two aircraft. So what's happening is they're merging together and they're coming close and they're coming close and they're also coming closer in altitude in the vertical domain. And this is a common problem in these merging conflicts, arrival merging conflicts. So go ahead and play the movie there. So you can see they've got about 3,000 foot of vertical separation. They're coming together now. They've got 8 miles, 6, 5, 4, 2 miles. Still have vertical separation. Still good. Again, this is our prediction of what's going to happen. And so now, right about now, we should have loss of separation as the two aircraft lose vertical separation. So this is the problem that has to be solved. So next slide. So here's the resolution. Why don't you go ahead and play that? I showed you what the resolution looked like earlier. So we turn the aircraft on the right. We turn him behind the red aircraft, and you can see that we've got 9 miles, 8 miles horizontal separation. We've still got vertical separation. In fact, I think we're going to lose. Okay, we've lost vertical, but we still have our 6 miles horizontal, so we're good. So the separation criteria, remember, it's 5 miles or 1,000 feet. Okay, so what I'd like to do now is I'd like to talk about the safety assurance function. Next slide. Oh, no, I'm sorry, I got ahead of myself. Okay, so this is a summary of the auto resolution results. Remember, I said that we ran the auto resolution logic that we've been developing against Cleveland Center traffic at 1 times, 2 times, and 3 times the traffic levels. So you can see there that the 24-hour traffic count rises from 7,000 to 26,000. The conflicts it's not quite quadratic with the number of aircraft, but it's not quite linear. So it's somewhere between So the point of this slide is that the conflicts detected and the mean delay associated with all of the resolution maneuvers does not really rise appreciably, and in fact it's acceptable. So the numbers on the bottom there show, if you compare the original trajectory with the resolution trajectory, you get mean delays of on the order of 20 to 25 seconds. And so this is considered an acceptable rise. So what does this look like over the entire run? Let's go to the next slide. So here's a histogram of the auto resolution delay characteristics for the 1 times, 2 times, and 3 times traffic. And you can see it's a fairly clean looking distribution. Where I'm showing here is the percentage of aircraft as a function of the minutes of delay, whereas the center bars are 0 minutes plus or minus 15 seconds. They fall into that bin. And then, as we go out to the right, I'm in the 30 seconds delay plus or minus 15, and 1 minute plus or minus 15. Interesting, you notice that to the left of center, some of the cases, there's not a delay, but an increase. Rather than delay, there's an increase in the speed, and that's partially due to the fact that aircraft that are descending, for example, and still holding Mach number will actually speed up. If they hold Mach number and while they're descending, they will speed up and get to the end, to the end of the trajectory sooner. Okay, now I'd like to go to the safety assurance. Okay, so this will be the last area I want to talk about. So I talked about the safety assurance function being something that is highly safety critical, and what we've been developing is a capability for analyzing, for building and analyzing very short-term trajectories for all the aircraft. The idea is that you want to look at multiple trajectories. You want to look at one trajectory that merges the aircraft position back onto its flight plan, and another trajectory that is based only purely on what the aircraft is doing independent of the flight plan. We're thinking, although we haven't done any work in this area, that there needs to be automated safety assurance maneuvers folded into this, but that will come in the future. Next slide. Okay, so I talked about multiple trajectories. Here's what it looks like in the horizontal plane. The 2 heavy dark lines are the short-term trajectories for the aircraft. The higher one, as you can see, is merging the aircraft back onto its flight plan route, and the other one is projecting straight ahead. So the idea is we want to be probing both of these trajectories for potential conflict against all other aircraft and their dual trajectories. Next slide. So here's the vertical case, and this represents a case where an aircraft is currently flying level, but it's been given an altitude change. In other words, it's been given an altitude amendment to climb to a higher altitude. So in this case, we need to probe the dead reckoning trajectory, the level trajectory, assuming that the aircraft isn't going to climb, because we don't know that he's climbing yet, so we have to assume that he's not going to climb. And then we want to probe a slow climb and a fast climb. And the gray area in this diagram really represents the region that we need to probe against. So in today's airspace operations, it's the conflict alert function, which is kind of a safety net for controllers. I talked earlier about in today's operations, if 2 aircraft are predicted to lose separation within a short period, like within 1 or 2 minutes, the data blocks start flashing. So the approach we've taken here is to try and compare the performance of our safety alerting functions with that of the conflict alert function in today's operations. Next slide. So what's an operational error? This is a plot showing the number of operational errors in our database versus the flight phase of the aircraft. First of all, let me say what's an operational error. Anytime two aircraft lose the legal separation, in other words, they come closer than 5 miles or 1,000 feet, and it is determined that that is due to an error in air traffic control. I mean, it's not a controller made an error or whatever. Then that is considered an operational error. In 2005, there were 1,500 operational errors in the NAS, and there are about 3 a week, and one of those 3 a week is really considered to be a serious error. And what does serious mean? It means that maybe the controller just didn't see something. He just missed an aircraft, or combined with the fact that the trajectory, like the closure rates, the trajectories were really such that there could have been a problem. So the main point of this slide is that if you look at I'm showing that of the 69 operational errors that we have analyzed so far, and this number is actually growing. This is another thing that has come out of our great relationship with the FAA. I mean, these kinds of data are just really invaluable in doing these analysis. The large bar on the left there shows that most operational errors involve aircraft in cases where one aircraft is descending and one aircraft is level. And in fact, 90% of the operational errors involve aircraft in transition. You can see that the level cases are really only 10%. And so that's really why that's a big challenge is looking at those cases. So okay, let me go on here. So what I'm going to show next is just a comparison of our safety assurance with the performance of the conflict alert function. Next slide. So for the 69 operational error cases, the graph here shows the percentage of alerts for both our tactical safety assurance and conflict alert as a function of the alert lead time. So as you can see, that for our tactical safety assurance logic, 70% of actual operational error cases, I mean these are cases that actually did occur in today's NAS, were detected with 30 seconds or greater before loss of separation, compared to the conflict alerting function, which caught about 30% of them. And you can see also as you go further out, and for the 60 seconds to go, we get about 45% versus 15%. So you might ask, what about that last 20% on the top? Why didn't we detect these? There are just some cases where a mistake is made and an aircraft is just immediately descended down upon another aircraft, and you just can't catch those because the aircraft just starts descending, and there are some cases where, so the challenge is to really detect these, develop methods to catch all these cases. Okay, so really, why don't we go to the next slide? I'm kind of starting to wrap up here. I've talked about kind of a few of the areas that we're working in, and this is by no means conclusive. We've done some simulation work. There are a lot of challenges ahead. The interoperability of these safety assurance functions, the primary safety assurance, the tactical safety assurance, and today's TCAS. How do those... I haven't talked about the modeling and measuring human awareness in automated systems. The challenge here is that we have higher levels of automation, which we need in order to accommodate capacity with safety. But the system needs to be designed in such a way that the human is always aware of what is going on in the higher levels of automation. And it needs to be designed in such a way that it is fail operational. I mean, we can't just hand the system back to a human controller with 30 airplanes and expect it to work like in today's operation. That just won't work. So failure and uncertainty modeling. That needs to be an important part of this. System integration for safety. How do all these functions play together in order that we have a safe and efficient system that meets the requirements? Improved and consistent metrics. I showed a few metrics here. We don't have them quite all integrated together yet. I mean, the other metric is how well are we actually doing the conflict detection. I don't have a metric for it. I don't have that really folded into our set of metrics. We want an improved and consistent set of metrics for all of the technical areas that we're doing. Those top two ones are really, those are foundational. Those are, along with the automated resolution algorithms, the top two are really foundational areas that we have NRAs in both of those areas as well as other areas. Comparison of the airborne and ground-based methods. Again, that comes out of the metrics. I mean, we're doing work in airborne and ground-based methods, but we need to compare those and see, using objective measures, where one is appropriate and where the other is appropriate. And finally, testing in today's operations. Our experience from the past is that we always learn a great deal from operational testing. So a big challenge is, how do we test some of this technology in today's operational environment? I know we'll learn more as we do that. So my final concluding slide, next slide. So really, the bottom line, the takeaway message is that today's airspace system will not support the future air traffic demand. Automation of the primary separation assurance function is needed, and the primary technical challenge is to identify technology and operations that can achieve these higher levels of automation while maintaining safety in nominal and failure conditions. So there were a lot of people that contributed to this work, and I'd just like to put a slide up here that kind of acknowledges their contributions. Thank you very much.
Hello, I'm J.D. Harrington. I'll handle the question and answer portion of today's presentation. Thank you, Dave. Before you ask a question, if you would, make sure we get the microphone to you before you start, and if you would introduce yourself as well. Right now in the audience, and we encourage questions as well from the centers that are listening in as well. Any questions we can get started with here?
Hi, I'm Terry Allard from the FAA Human Factors Program Director. Just wondering, Dave, it's very interesting and very nice talk, thanks. I was wondering what your thoughts were with respect to roles and responsibilities between ground-based and cockpit. What's the role of the pilot in the future automation systems?
I think the pilot will be making use, will play a greater role in various functions within separation assurance. I think they'll play a greater role. I think data link communication, cockpit display of information, I think the role is going to be greater. I'm not sure what level, whether they're going to take on the full responsibility. I don't know. That's what we need to find out. But I think they're going to have a much greater role in the separation assurance functions.
Okay, question here from Dr. Griffin.
Yeah, Dave, that was interesting. As a frequent user of the system you're talking about, not as frequently as I would like, by the way, but consistent with my job requirements, it has always occurred to me, or for a long time it has occurred to me, that this is a self-inflicted wound. Some of what we do is because our air traffic control structure routes people along defined routes. Okay, until you get to the core areas where everybody's trying to land, and now you have a different problem. But a lot of the stuff you showed was en route air traffic control, where people are going along defined routes. If given the existence of microprocessors, and whether you're talking about GPS or traditional VOR and TACAN nav aids, if you would just if the air traffic control system were designed to let people fly from where they are to where they wanted to be, then in a statistical sense, you would have far fewer incidents to avoid, and they would therefore be more avoidable. And an air traffic control system based around that different concept would yield, I think, a vastly different result.
We are definitely looking at that. I mean, the trajectory automation technology by no means requires that aircraft fly on fixed routes. And that is something we're looking at. In fact, we have some results in that area to suggest that if we let aircraft fly on their direct wind routes, for example, and we do that same separation assurance metric, we get very consistent results. So I think there's data out there to suggest what you're suggesting is that there's...
If we're going to go to an NGATS world, I guess what I'm saying is we should rethink the whole thing, because we're already, tearing up an awful lot of paper. Why not just start fresh?
One of the metrics that I want to use is, I can compare what do my metrics look like when aircraft are on their defined routes compared to what if they're all just fly them all on wind routes, every one of them, independent of air traffic restrictions that are generated by sector boundaries and various other things. What do my metrics look like then? And I didn't really talk about it, but in some of the work we did in those 5 airspace sectors, the sector boundaries just played absolutely no role in the automation work that we did. In other words, it just didn't matter that they were there. So the restrictions associated with routes that go around sector boundaries, I think we can eliminate those, and that's something that we are definitely looking at.
I'm going to have to yield to my desire to ask yet another question.
Please do.
You showed up in your comparison of with and without air traffic control. I counted out. I realized it was for a 90-minute period, and I realized it was only in one segment. But you were basically avoiding 13 conflicts. I counted up your histogram.
Okay.
Which you probably have not done. But you were basically, so another way to interpret all this is this whole air traffic control morass in which we who fly find ourselves embedded is designed around avoiding, for this segment of time and that segment of space, 13 conflicts. I mean, I feel like I want to say, stop me before I kill somebody.
Yeah, the metrics are better within the automation.
The metrics were hugely better within the automation, but not only that, it's like the whole air traffic control system is designed around avoiding a minuscule number of conflicts in a sea of aviating blobs.
Yeah, there's plenty of airspace out there.
Right.
In fact, in that, the diagram I showed at the very end, where you see the characteristics of the 1 times, 2 times, and 3 times traffic, there's no difference. We're not hitting any walls. There's plenty of airspace out there.
Self-inflicted wound.
Yeah, yeah.
All right, any other questions here at headquarters? All right, one here in the 3rd row.
Hi, Murray Hirschbein from Aeronautics. It was interesting to see that as you increased the traffic 2-3 times, you were able to reduce the conflicts to just more like linear or sublinear increases. Did you try that at all by throwing in some of the adverse weather conditions, the maybe unpredictable thunderstorms that pop up, or just random stuff?
That is part of our technical plan, absolutely. But we haven't gotten to the point where we're merging the conflict resolution problem with the severe weather avoidance problem.
The part that I'm getting at goes a little bit maybe back to what Terry Allard was saying. You're going to reach a point maybe when the weather is moving around and causing the interruption to be at a rate that maybe the human cannot respond to.
Yeah.
Because you don't know where it's going to go and you can't predict. You have much to worry about as trajectory of the weather as you do of the aircraft, which you can't control. And is there a point at where even your automation system will not be able to respond to the frequency of updates that have to be made?
I think the challenge is to identify, to the extent we can, is the characteristics of the weather that show that we're getting into a state like that. And then we need to start diverting aircraft. We need to identify, and that's not only weather, but it has to do with traffic complexity. When is the complexity of the airspace, whether it has to do with weather or whether it has to do with the number of aircraft that are coming together, when is it reaching the point that the uncertainty level is so high that we might get ourselves into a bind that we can't get out of? And determining when we might be getting there and then taking actions, rerouting actions, that also is a key part of the work.
Okay, we have time, just a little time for one or two more questions. All right, I believe we have a question at Glenn right now.
This is Bob Hendricks. I just had a question about your satellite to aircraft communications. You spoke a lot about ground to aircraft and aircraft to aircraft communications, but not anything on the satellite to aircraft and aircraft to ground communications. Could you elaborate on that?
Sure. I guess I'm not an expert in that area, but I think that is one way of accomplishing the data link communication, whether it goes through a satellite or something else. I guess I view that as a data communication, one data communication capability. The key requirement is to transfer the information between the air and the ground and between the air and the air. Now, for air-ground, how that works, whether it goes through a satellite or some other mechanism, as long as it meets the performance requirements of the separation assurance and traffic flow management system.
All right, we also have one more follow-up question from Glenn. I'm sorry, we have a question from Dryden.
Hi, Dave. This is Rod Bogue at Dryden. I had noticed your picture at the beginning, your chart that showed the rapidly increasing traffic. This seems like this is a juggernaut that we got to get out of the way of at some point. I guess I'm wondering, do you have any thoughts as to how much time we can take to try to get this problem put together and start showing some operational benefits, when that's going to have to happen so that we don't impact the traffic capacity that we need to have?
Oh, that's a tough question. I guess let's say we have double the traffic in 20 years. We ought to be starting to put some of this stuff in place, and I'm not the best one to answer these kind of questions, but I'll take a shot at it. We should be starting to put some of the capabilities in place in 5 or 10 years. And it's not all going to happen at once. I mean, we put capabilities in, we learn, we put more capabilities in, we learn, we make changes. I mean, I think that's the best I can do, Rod.
Sorry, David. We have one question also from Glenn.
And you mentioned that most commercial aircraft have the anti-collision systems. Which ones don't? I don't want to fly those.
I believe, and someone here could probably correct me, I think any aircraft with a passenger capability of 19 or more isn't required to have TCAS. I'm not sure if I have that number right, but
all right, are there any other further questions? All right, well, that's going to conclude today's presentation. I'd like to extend appreciation for all the support from David McNally. Thank you very much. And if you'd like more information on NASA's aeronautics programs and projects, please join us on the web at www.aeronautics.nasa.gov. Thank you.